In the last lecture, we have studied the vector diagrams of LS coupling and JJ coupling. Now today in this video, I am going to explain interaction energies of LS coupling. So LS coupling we have already discussed in the one valence electron system also, and there we have already derived an expression for interaction energy. So this interaction energy, as we have discussed earlier, is responsible for fine structure in the spectra of one valence electron system. Now in this third chapter, since we are studying two valence electron system, so here also LS coupling is dominant, and because of this LS coupling, whatever the interaction energies involved because of LS coupling, these interaction energies are responsible for fine structure in case of two valence electron system. So in this video, I'm going to explain these interaction energies of LS coupling for two valence electron system. So due to interaction between orbital motion and spin motion of electron, there is a change in total energy of the system. So this change in total energy gives rise to fine structure of the spectral lines. So for one valence electron system, as we have discussed earlier, there is only one electron. So the spin motion of that electron and the orbital motion of that electron, so there is an interaction between these two kind of motion and the related momenta vector, that means orbital momentum and spin momentum of the one valence electron, and that will result a change in total energy of the system, and that change in energy will result into a fine structure. But now when we talk about a two valence electron system, there are two electrons. So each electron has its own spin motion as well as orbital motion. So you can say there are four such vector quantities: spin momenta of two electrons and orbital momenta of two electrons. So two vectors representing separate spin momenta and two vectors separately representing the orbital momenta. So there are four vectors, and there can be different interactions among these four vectors. So that interactions we are going to consider here. The two valence electron system, as I have told you, are having four angular momenta: L1 star, S1 star. So L1 star represent the orbital momenta, S1 star represent the spin momenta. Similarly, L2 star and S2 star represent the orbital momenta of second electron and spin momenta of second electron. So there can be six possible interaction among these four vectors. How? Let us see. So first interaction, the spin moment of first electron interacts with spin moment of second electron. So this is the first kind of interaction. Then second one, the orbital moment of first electron interacts with orbital moment of second electron. Then third interaction, the orbital moment of first electron interacts with spin moment of first electron. Then next interaction, the orbital moment of second electron interacts with spin moment of second electron. Next one, orbital moment of first electron interacts with spin moment of second electron. And the last one, that is sixth interaction, the orbital moment of second electron interacts with the spin moment of first electron. So these are the six possible interaction one can say which can be possible here in case of two valence electron system, because of these four quantities or four different types of angular momenta: orbital momenta and spin momenta, two orbital momenta L1, L2, and two spin momenta S1, S2. So these are the six possible interactions. Now let us concentrate ourselves on these six possible interaction, and we shall discuss about these interactions, and let us try to define the interaction energies here of LS coupling. Now earlier in the second chapter, we have already derived the derivation which represent the shift of each fine structure, and it is given by so because of the interaction energy, this shift is observed, and that is given by this expression: minus delta gamma Lx that is equal to gamma, and that is equal to a L star S star cos of L star S star. So this particular term shift represented by gamma, that gives you the fine structure, and this fine structure actually it is a change in energy, that is because of the what we call the interactions or the interaction energy involved among these particular momentas, different momentas. And one can just see this kind of equation we already derived, the term shift that is equal to a this L star S star cos of L star S star by cosine law, that can be replaced by J star square minus L star square minus S star square divided by 2. So these equation we already derived in the second chapter while studying the one valence electron system. Okay, so we can use this equation for the 6 interaction. Just now we have defined here among those 4 momenta vectors, and the 6 energy relations we can derive from this particular using this equation here. Okay, so we shall apply this equation for a term shift to our interactions we have represented through the 4 angular momenta vector, that is L1 star L2 star S1 star S2 star. So let us see these interaction energies. So first let us define by term gamma first, this first term shift gamma first, that is equal to A1 S1 star S2 star into cos of S1 star S2 star. So we shall use this kind of equation here. So first interaction is among S1 and S2. Okay, S1 and S2. Therefore this equation we can modify as gamma 1, that is equal to A1. So A1, instead of L and S we have S1 S2. The interaction is between S1 and S2. So therefore L and S you can just replace by S1 and S2. So gamma 1, that is equal to A1 S1 S2 S1 star S2 star cos of S1 star S2 star. Here we have L and S. Instead of that, since interaction is between S1 and S2, so we can replace it by S1 star S2 star. Okay, so this is the first definition or first kind of term shift because of the 6 possible interaction, the first out of the 6 possible interaction. So second term shift represented by gamma 2, that will be equal to A2. Now the second interaction we have defined between L1 and L2. Therefore A2 L1 star L2 star cos of L1 star L2 star. The third interaction we have represented between L1 S1. So the term shift gamma 3, that is equal to A3 L1 star S1 star cos of L1 star S1 star. Next one, this gamma 4, that is equal to A4. Now next interaction is between L2 S2. Therefore A4 L2 star S2 star cos of L2 star S2 star. And the fifth interaction is this gamma 5, that is equal to A5. So fifth interaction is between L1 and S2. Therefore A5 L1 star S2 star cos of L1 star S2 star. And the last interaction we can say terms this gamma 6, that is equal to A6. Now this interaction is between L2 and S1. Therefore we can write A6 L2 star S1 star cos of L2 star S1 star. Okay, so we have defined these 6 possible interactions, and these are related to the fine structure. Okay, so let us make some assumptions which are based on theory. So what are these assumptions in order to consider the actual interaction energies? So according to classical model of precision of vector, you know, any particular physical quantity or a vector, it is said to be precise in certain field, force field. Okay, for example the motion of a top in gravitational field. So just like that, the according to classical model, the precision of vectors, each spin, that means S star, and each orbital momenta, that is L star, produces its own field. Okay, the other vector tend to carry out a larger precision around this field. So because of any particular motion, it may be spin motion or orbital motion, so it has its own field, and when the other vector uh, perform its motion in the first vector, then there will be a kind of precision of the vector that is called as Larmor precision around the field due to first kind of portion. So this particular Larmor precision is important here. The rate of precision is different for different vectors. So if you consider the precision of one quantity which is actually present in uh, along with the second quantity, then in that particular case the rate of precision is different for different vectors, and depending on this rate of precision, the vector which is precessing more rapidly has predominating interaction over the other. So whichever the vector which is precessing more rapidly, it has predominating interaction over the other vectors. So you can just compare between the particular kind of precision or rate of precision for different vectors, and from that one can say which particular interaction has predominating nature. Now LS and JJ coupling, it is observed that they give good agreement with experiment. So here we shall consider only LS coupling, interaction energy due to LS coupling. In case of LS coupling, as we have already seen, that the interaction energies gamma 1 and gamma 2 are predominating over gamma 3 and gamma 4. Okay, so why it is predominating? Because the rate of precision for gamma 1 and gamma 2, whatever the quantities involved, which quantities are involved for gamma 1 and gamma 2, just now earlier we have seen these equations, you can see here. Okay, gamma 1 and gamma 2. So gamma 1 and gamma 2, the vectors involved are S1 S2 and L1 L2. Okay, so because of this, these vectors are precessing more rapidly. Okay, therefore they are predominating over these particular vectors L1 S1 and L2 S2. Okay, so let us come to the our current point of discussion. So the LS coupling, the interaction energy term first, gamma first and gamma second are predominating over gamma 3 and gamma 4. That means here the rate of precision for those particular vectors involved in the gamma first and gamma second must be higher or dominating over this gamma 3 and gamma 4. Whereas this gamma 5 and gamma 6, the 6 equations we have just written in order to represent the interaction energy. So out of that, this gamma 5 and gamma 6, they are negligibly small, because whatever the vectors involved there, the rate of precision may be too small. So they are very weak, you can say they are negligibly small. Now let us consider some of these particular terms, the 4 terms which we have mentioned here, that is gamma 1, gamma 2 and gamma 3, gamma 4. So we have already defined according to the formula, gamma 1 is equal to A1 S1 star S2 star cos of S1 star S2 star, and gamma 2 is A2 L1 star L2 star cos of L1 star S2 star, and these are the two term values represented by gamma 3 and gamma 4 for the vectors L1 S1 and L2 S2. So gamma 3 is A3 L1 S1 star cos of L1 star S2 star S1 star, and gamma 4 is A4 L2 star S2 star cos of L2 star S2 star. Okay, so let us apply the cosine law of triangle for these particular vectors, and from the cosine law of triangle, this kind of derivations we already studied in the first chapter, so I shall not be repeating here all the details. You can refer to that particular derivation which we have discussed in the earlier chapter, that is the one valence electron system. So according to cosine law here, S1 star square will be equal to this S1 star square plus S2 star square plus 2 S1 star S2 star cos of S1 star S2 star. Okay, so from this we can write here S1 star S2 star cos of S1 star S2 star, that is equal to, if you rearrange the term in the earlier equation, it will be S1 star square minus S1 star square S2 star square upon 2. Okay, so you can say instead of S1 it should be S only. This is a slight correction you can just consider here. This capital S represent the spin momenta for the entire atom, and that should be having no suffix at all. It should be S star square only here. Okay, so by just rearranging the term, we can write here this gamma 1 is equal to 1 half A1, this S star square minus S1 star square minus S2 star square. So this 1 by 2, it is considered 1 half, and the constant we have substituted here is A1. Okay, so A1 is a constant, and what is that constant, that later on we are going to define. Similarly, for the gamma 2, we can write 1 half A2 L star square minus L1 star square minus L2 star square. Now, since the angle between the vectors is continuously changing, which vector? Whatever the two vectors involved here, for example, here S1, S2 or L1, L2, the angle is continuously changing, and therefore the average value of the cosine term here, that must be evaluated. And in order to evaluate this particular average value, certain trigonometrical laws and the projections of the vectors, they are considered. So all these details we are not going to discuss here. I will just take those relations simultaneously. So using the theorems in trigonometry, we can define average value in terms of the projections. And for example, here cos of L1 star S1 star, you can define as cos of L1 star L star into cos of L star S star into cos of S star S1 star. And another value, average value of cosine function, cos of L2 star S2 star, average value of cos of L2 star S2 star, that is equal to cos of L2 star L star, cos of L star S star, and into cos of S star S2 star. Okay, so it is assumed that the two quantities S1 star L1 star, they precess more rapidly than these two vectors, that is L star S star. Hence their component normal to the respective axis of rotation will be cancelled out. So here I have not shown the actual diagram of these particular vectors, but remember, when these are precessing more rapidly than L star S star, then their components normal to the respective axis must be cancelled out. Okay, now once again, using cosine law and average values of cosine, we get here these average values and cosine law we can further simplify, and we will get here by just performing the addition of the two equation for the gamma 3 and gamma 4. We can write here A3 alpha 3 plus A4 alpha 4 in the first bracket into L star S star cos of L star S star, and this can be simplified as, so if you substitute for this L star S star cos of L star S star, that is equal to 1 half J star square minus L star square minus S star square, and this term remains as it is. This is the constant A3 alpha 3 plus A4 alpha 4. Now if you consider this, where A3, this constant is S star square S1 star square minus S2 star square minus S star square divided by 2 S star square into this L star square minus L2 star square minus L star square upon 2L star square. So this is the relation that actually we have substituted here for A3. Similarly, we have also substituted for A4, and the value is like this: S2 star square minus S1 star square minus S star square divided by 2S star square into L2 star square minus L1 star square in minus L star square divided by 2L star square. Okay, so these are the values of alpha 3 and alpha 4 for any given triplet. Triplet means what? S is equal to, capital S is equal to 1. Okay, multiplicity of states. So 2S plus 1, that will be equal to 3. Therefore, it will be called as triplet for S is equal to 1. So for any given triplet, S1 star, S2 star, L1 star, L2 star, and S star and L star are fixed in magnitude. Therefore, A3, A4, alpha 3, alpha 4 are constant. Okay, A3, A4 and this alpha 3, alpha 4, they are constant. So if you substitute this constant as A is equal to A3 alpha 3 plus A4 alpha 4 and so on, so let us treat it as a constant A. Therefore, the equation for term 3 gamma 3 plus gamma 4, that will be A L star S star cos of L star S star plus 1 half A, okay, this A into J star square minus L star square minus S star square. Okay, so the complete expression of energies can be obtained by evaluating A coefficient. So we need to evaluate this A coefficient if you want to find out the complete expression for energies, and this is needed. One just have to evaluate this value of the constant, then only we can talk about the complete expression of energies. Okay, so the Spin orbit interaction are due to electrostatic effects. Spin motion and orbital motion. So there is an interaction, and this interaction is governed by the electrostatic effects. The singlet levels lie above the corresponding triplet level. Therefore, A1 of gamma 1 is negative. Okay, so these terms one must consider certain conditions. For example, here this A coefficient. So spin orbit interaction are due to electrostatic effect, as we know, and the sunlight leaves the singlet levels lie above the corresponding triplet level. Therefore, A1 and gamma 1 are negative. A1 of gamma 1 is negative. Okay, let us consider now one example of PD configuration. Okay, so PD configuration of two valence electron system. So one electron is in p orbital, other is in d orbital. So first electron which is in p orbital, what is the value of L? So L1 is equal to 1, and second electron which is in d subshell, so L2 is equal to 2 here. Okay, L2 is equal to 2, you can see here, and both S1 and S2, the spin quantum number, as you know, it has a value half. So S1 is equal to half, S2 is equal to half. So we know these four numbers, quantum numbers, you can say. So the equation for gamma 1 is given by gamma 1 is equal to 1 half A1 in bracket S1 star square minus S star square minus S1 star square minus S2 star square, where S1 is equal to half, S2 is equal to half, and S is equal to 0 or 1. And S can have two values, 0 or 1. Okay, because S1 is 1 half, S2 is 1 half. So quantum mechanically, the values allowed for S are the small s1 plus s2 up to small s1 minus s2. So half plus half, that is 1, and half minus half, that is 0. So between 0 and 1, all the values, integral value. So there is no other value. So 0 and 1, s is equal to 0 and 1. Okay, so s1 is equal to half, s2 is equal to half, the spin quantum number. Now we can use this value, and s is equal to 0. S can have two values, see here, 0 or 1. For s is equal to 0, the singlets gives the singlets, and s is equal to 1 give the triplets. So when s is equal to 0, what does it indicates? S is equal to 0, that indicates that the two spin momenta vector, they are opposite to each other and they are equal in quantity. So you can say here the s1 is equal to half, s2 is equal to half, therefore s is equal to 0 or 1. For s is equal to 0, gives the singlet, and s is equal to 1 gives triplets. So the special comment about the particular terms involved here. Okay. Now let us try to evaluate for s is equal to 0. So for s is equal to 0 term, this particular gamma first, that will be equal to 1 half a1, and just substitute these values, s star square. Now s is equal to 0, s star, it can be given by under root in bracket s in bracket s plus 1. Okay, under root of s in bracket s plus 1. So s is equal to 0. So under root of s, that means 0 in bracket 0 plus 1. Okay, 0 into anything, that is 0. So therefore this quantity is 0. Now second term, that is this particular s is equal to 0. Okay, we can see now the value of s1 star. So s1 star square under root of s1 in bracket s1 plus 1. Okay, so under root of s1 is what, half, and s2 is also half. So s1 under root of s1 in bracket s1 plus 1. So s1 plus 1 is 3 by 2 into 1 half, that is 3 by 4. So therefore root 3 by 4 square, and this is also root 3 by 4 square. Okay, so this is what the equation for term first. Similarly, we can write the value here if you substitute the values. Okay, now see here, root 3 by 4 bracket square. So that will be root 3 by 4 minus 3 by 4 minus 3 by 4. So minus 2 3 by 4, and you can see here that will be minus 3 a1 by 4. Okay, minus 3 a1 by 4. So that is the value of first gamma value, term 1. And another possible combination for s is equal to 1, if you substitute the same here, 1 half a1, as it is in bracket. Now this should be root 2, that will be root 2 square. Okay, root 2 square minus under root of root 3 by 4 square minus root 3 by 4. These two terms will remain as it is, and here we have root 2 square. Okay, so if you substitute these values here, this is 3 by 4, this is 3 by 4, and this is 2. Okay, root 2 square, that will be 2 here. So if you substitute the values, then you will find that this first gamma value, gamma 1, that will come as a1 by 4. So 1 half a1 into 2 minus 3 by 2. So 2 minus 3 by 2, you are just considering this particular relation here, and therefore term first gamma 1, that is equal to a1 by 4. Okay, so see here, the first coefficient is this, and this is the second question. So minus 3a1 by 4 minus plus a1 by 4. So if you see this, it is according to the particular concept here. Okay, so the equation for gamma 2 is equal to 1 half a1 l star square minus l1 star square minus l2 star square, and here L1 is equal to 1, L2 is equal to 2. Therefore the L values, L2 plus 1, L1 up to L2 minus L1. So L2 plus 2 plus 1, that is 3, and 2 minus 1, that is 1. So from 1 to 3, all the values of L are involved here, and they represent the terms P, D, F according to the value of L, that is 1, 2, 3. Okay, so for L is equal to 1, gamma 2, you can see here these particular terms. Okay, so L is equal to 1, 2, 3. Now first condition that we are going to consider is L is equal to 1. So gamma 2 will be equal to 1 half a2. Now L, you have to substitute 1 here, therefore under root of L in bracket L plus 1. Okay, so that particular quantity one must consider here, L in bracket L plus 1. So if it is 1, 1 plus 1, that is 2, 2 into 1, that is 2. So it is root 2 square. So gamma 2 is equal to 1 half a2 root 2 square minus root 2 square minus root 6 square. So this root 2 and this root 2 square, that will get cancelled, only root 6 square. Okay, so root 6 square is 6, so that will be minus 6. 1 half a2 into minus 6, that will be minus 3a by 2. Okay, that is also correct now. Similarly, L is equal to 2. If substitute the values here, L is equal to 2. So you can see here, gamma 2, that is equal to 1 half a2 root 6 square minus root 2 square minus root 6 square, that is equal to 1 half a2 into minus 2, or gamma 2, that is equal to minus a2. So like this, you can just simplify the equation. L is equal to 3 r2 1 half a2 in bracket this root 10 square minus root 2 square minus root 6 square, and if you simplify this gamma 2 will be equal to twice a2, that will be twice a2. So the values are gamma 2 are, you can see here, minus 3a2, minus a2 and 2a2. So these are the values of gamma 2, and we have to use this while representing the fine structure. Okay, now this is the fine structure for PD configuration here. See, the value of gamma 1, a1 by 4 and minus 3 a1 by 4. So these are the first values which represent the first splitting for imaginary central line. You can see this is the imaginary central line. Okay, and from this how much it is deviating, first shift is given by minus 3 a1 by 4 and a1 by 4. Now second splitting occurs here. You can see once it comes here, there are 3 splittings, minus 3a2, minus a2 and 2a2. So these are the 3 special you can say representations here in this diagram. So same coefficients you can see here, minus a2, minus 3a2 and 2a2. Okay, so these are the quantities which are represented here in this particular diagram, and this S is equal to 0, therefore singlet, and S is equal to 1, therefore triplet here. Okay, so this is how the different terms here for PD configuration which we have already derived. You can see 1p1, 1d2 and 1f3. These are the singlet terms and these are all triplet terms. Okay, so in this video actually you can see the splitting of fine structure. Okay, this is the initial splitting because of term first, and these are the three constant. L is equal to 1, 2, 3, minus 3a2, minus a2, and 2a2. These are because of the second splitting. We can say second splitting, that means the second quantity here. Okay, term second or gamma 2. So this is how in this video we have come to a conclusion that there is a fine structure splitting, you can see here, because of the LS coupling and the 6 possible interactions we have considered here. Okay, these 2 into these 3, you can say 6 possible interactions, and this, according to this interaction, you can observe the splitting here. First splitting here and second splitting here. Okay, so the actual terms, they are represented here, and what we are going to do is that the same discussion I will be continuing in the next video, but at that time we shall discuss more about this particular diagram. Okay, we shall discuss more about this diagram.